Hello everyone and welcome to the course Design Borefields with Confidence. This is part 1, chapter 1, Why should you install a ground source heat pump? Because before we start talking about the design of borefields, we have first the question, why should we install a ground source heat pump in the first place? Because, let's directly name the elephant in the room, the investment cost is rather big, and geothermal borefields have the history of being an expensive technology, especially when compared to air source heat pumps. So why should you install a ground source heat pump? Now, there are a couple of reasons for that. There are individual reasons. For example, you have your efficiency. You have the efficiency versus the operation cost. We have defrosting problems with air source heat pumps. You have the thing of effective cooling, lifetime maintenance, and aesthetic and noise. These are all individual reasons why you as a building owner would rather choose a ground source heat pump instead of an air source one. But on the other hand, we have also collective reasons why we as a society should really push forward with the geothermal solution, which on the one hand is the problem of urban heat island effects, and on the second hand, the problem of net congestion. Now, let us just go through this so you know why a ground source heat pump is a good idea in the first place, so it makes sense that you also care about the design of these systems. Now, when we talk about the efficiency of ground source heat pumps, we typically know that they are better than air source heat pumps. Now, the concept of efficiency, as we will discuss later in this part of the course, is that it depends on the source and the supply temperature. And typically, our ground temperature is warmer than our air temperature in winter, whereby our ground source heat pumps has a better efficiency than our air source heat pump. So yeah, it typically has a better efficiency. And that's also because ground source heat pumps, they are not just taking energy out of the ground, it's also seasonal thermal energy storage. It's to say, typically in summer, we're also injecting heat back into the ground in order to keep the ground temperature more or less level. And we will cover that in way more detail throughout the rest of the year. But the problem is that, yes, indeed, if you look at the official data, ground source heat pumps were historically way better than air source heat pumps. But the technology of air source heat pumps also did evolve, and now on paper they're almost more or less the same. Now, there is a problem on paper because typically the efficiency of a ground source heat pump is given at B0W35, meaning 0 temperatures out of the ground, the 35 degrees going into the building. But this is typically an underestimation of the borefield temperatures. If you design your borefield accurately, these 0 degrees will perhaps be after a couple of years and only at the peak moment or the most critical moment in the year, not on average. So that's also a little bit of vagueness there, which we will also shine some light on in a couple of next chapters. And then we also have the problem of climate change and the concept of seasonal efficiency. Because yeah, perhaps at the coldest time in winter this reasoning holds and our ground source heat pump is more efficient than our air source heat pump. But in mid-season, when it's 15 degrees outside and we want to heat it up to 20 degrees Celsius, probably our air temperature is higher than our ground temperature and our air source heat pump is more efficient. So with climate change and everything heating up, perhaps our air source heat pumps are automatically becoming more efficient than our ground source heat pumps. So on the efficiency standpoint, there's quite a lot of discussion, and depending on how you look at it, ground source heat pumps are, I believe, still on average, if you take everything into account, higher or better in efficiency, but air source heat pumps are rapidly taking over, and depending on where you live in the world, perhaps they are already more suited for heating your building. Now, efficiency is only part of the story because in the end, we don't really care about efficiency, we care about operational cost. Now, previously this was one-on-one linked because there was one electricity price, day and night perhaps were different, but At least it was constant. Now there are dynamic electricity prices with a price per hour or even quarter of an hour. So this means that it's not only important what your efficiency is, how much electricity consumed, but also when you do it. And here our ground source heat pump has a real advantage, because when there is a high demand for electricity and there is low production, then there are high prices, just the way economics work. And in the winter, when it's cold and dark, there is quite a lot of demand for heating, but the renewables and the dunkelflaute, they do not produce as much electricity as in summer. So there is also not so much supply of electricity. So the prices, they rise significantly when it's really cold outside. And it's here, when it's really cold, that we know that our ground source heat pump will be better. So our efficiency is here better, and also our prices are higher. So therefore, we really want this efficient technology because we care at that moment how much electricity we consume. And in the autumn, the spring, in the mid-seasons, there is quite a lot of electricity production. And there is some more wind, some more solar energy available. So perhaps our air source heat pump is now more efficient, but it does not matter that much, if you know what I mean. Because when the electricity prices are not so critical, your efficiency is not so critical. So this puts another perspective on our efficiency debates. Because if you take these dynamic electricity prices into account, which you can also balance out with battery technology, etc., so it's even more complicated, it does not really matter what the seasonal efficiency is. It does matter what your efficiency is at critical times, and there a ground source heat pump inherently is the better choice. Now, another issue, let's say, with air source heat pumps is the defrosting cycle. So when an air source heat pump is heating your building, it's taking the energy out of the air. And when it's cold outside, or it's 2 degrees Celsius, for example, it cools down the air and the moisture freezes to the heat exchanger in the air source heat pump. So this means that from time to time, the heat pump has to reverse its operation, actually heat the heat exchanger to melt the ice away in order to be able to keep functioning. Because when everything is freezed down, there is no way for new air to pass through and to exchange heat. So this defrosting cycle, it consumes electricity, but the other problem is that when it's defrosting itself, it cannot deliver heat to the building. And when you have a big building and you have quite a lot of heating demand, and these heat pumps, they shut down in order to defrost themselves, it's possible that you need to install extra capacity in order to be sure that you have your peak demand met. Because if your heat pumps are turning off in order to defrost themselves, perhaps your comfort levels are not met. So that's always something to keep in mind when cold seasons, that your peak heating demand can actually be met with your air source heat pumps as well, taking into account these defrosting cycles. Now, when we talk about effective cooling, ground source heat pumps also have an advantage. Now, we already mentioned the concept of seasonal thermal energy storage, where we're not only taking energy out of the ground, but we can also store it back into the ground. And this is completely different with the outside air. If we take energy out of it, the air cools down. And in summer, the air is gone. There is wind, the air is gone. There is no storage of energy there. But in the ground, if we extract the heat from the ground cools down. And this cold, this stored cold, we can use for passive cooling or free cooling in summer. And by this we mean that we don't need our heat pump for cooling. We just circulate a fluid through the ground. And since our ground is at 10, 12 degrees Celsius, we can use this cold directly to cool down our building in a passive way, which is also almost free. It is a very, very high efficiency because only a circulation pump is running to keep the fluid flowing through the borefield. Now, if you live in a warmer region, perhaps this passive cooling is not enough to meet your comfort levels. Then it's also possible to work with active cooling. So we turn the heat pump back on, but instead of like with a traditional air conditioning, blowing the heat out into the environment, we're going to put the energy all in the ground. So we're going to store it there to be used in winter. And the advantage of this active cooling with geothermal systems is that typically our ground temperature is colder than our air temperature when it's really hot outside. So also here, it's more efficient to cool with our ground source heat pump because it has to do less effort in order to get the energy to the ground than our air source heat pump has to do to get it out into the environment. And a bonus, the energy is stored for winter, so we have a higher ground temperature in winter, which is beneficial for both our efficiency and our operational cost at peak times. Now, talking about lifetime and maintenance, it's a little bit vague and depends from manufacturer to manufacturer, but typically air source heat pumps, they have a lifetime of between 15 to 20 years. And that's because they are outside. They face the weather conditions, snow, ice, rain. They're more prone to leaks because of this. And they also are placed sometimes in aggressive environments. For example, if you live nearby the coast, there's quite a lot of salt in the winds, and this can cause the heat exchangers to corrode. So you have to install special heat exchangers that can cope with this, which is also more expensive. Now, a ground source heat pump, it's installed safely in-house, facing the weather conditions, so it has also a better lifetime, typically around 25 years. Now, I also want to say that now with the movement towards propane machines, some manufacturers, like for example Weishaupt, has opted for creating ground source heat pumps that are placed outside. Because propane is a flammable and explosive gas, there has to be solutions for that, so some manufacturers choose to vent their heat pumps, to place them in an under pressure, so in case of a leak, the propane is evacuated out of the building. Weishaupt has opted for the solution of just placing the whole heat pump outside of the building, so there is no problem with leaks or explosive conditions there. And lastly, aesthetics and noise. Ground source heat pumps typically, as said, have no outside unit, and there is also no ventilation noise of the ventilator running, which, if you think about it, on a societal level, is really becoming a problem in some cities where there is quite a large zzz in the summer due to all the air conditionings running. And this brings us to also our first collective societal reason why we should opt for a ground source heat pump. Because when we have all air source heat pumps outside, the heat is not gone. We blow it inside the environment. And already our cities, as you can see on this graph, are rather warm. There is concrete, there is asphalt, and the heat is really trapped in summer inside of our cities when compared to the rural areas. And since the heat is trapped in these cities are typically 5 to 10 degrees warmer than the rural areas outside of the city. And when we install air source heat pumps on our facades and we blow the energy in the city is becoming warmer. But when our city is becoming warmer, also more of this heat is again going into our buildings through our windows and to our walls, meaning that our air conditionings have to work even harder, making the city even warmer. And also because the city is becoming warmer, the efficiency of our air conditioning units, of our air source heat pumps, is dropping. So this is a vicious circle where, there is no real good solution. And when we would use ground source heat pumps in this case, the energy is stored on the ground. So we do not dump the heat into the environment, and we can try to keep the cities a little bit colder in summer as well. And the second societal problem is the problem of net congestion. And this basically means there is no more space, no more capacity available on the grid for new connections. Meaning, you as a homeowner have only a limited amount of capacity, a limited amount of power you can get from the grid, because otherwise the system would fail. And in the Netherlands is already a big issue. There are places indicated in red where it's just infeasible to, for example, install PV panels because the electricity cannot be put onto the grid. You can't install charging for your electric car. You can't install a heat pump as well. So that's a really big problem, and it's occurring in more places around the world. And here, a ground source heat pump is also a better solution, let's say, than an air source heat pump, because this whole net congestion problem, it's a problem of peak powers. And at peak time, when it's really cold, our ground source heat pumps are more efficient. So they consume less power, they need less power to operate at these peak moments, which is really good for your whole electricity grid in general. So as a society, having more ground source heat pumps is also taking part of the pressure away on the electricity grid operator. And basically everything I mentioned here, from the higher efficiency, from the passive cooling and so forth, it's only true when the borefield is designed correctly. Then we have a long lifetime of the system, we have a good efficiency and low operating costs. And it's also when it's correct designed that the elephant in the room, the capex, is going to go away. Because more and more air source heat pumps are also becoming expensive because they have the same legislation related to refrigerants flowing through them. They have strong legislation related to noise, so sometimes you have to take measures to keep the noise down, which also costs money, etc., etc. So if you design your borefield correctly, especially for bigger projects, perhaps they come close to the capital expenses, the investment cost of our air source counterparts, which is really, really interesting. So design is important. Both the ground source heat pump as well as the borefield should be designed correctly. And in our next chapter, we will discuss this design in more detail. Why should we care about the design and how should we do it?